I'll be talking about a proxfun package, and for those who aren't familiar with it, I'll explain what it is. Before I explain what it is, I wanted to give a sort of overview of the motivation behind, well, proxfun in specific, but these types of packages in general. So the basic idea is we want to be able to manipulate functions and solve differential equations without having to worry about discretization, details, and so on. So the idea is to abstract away that sort of thing. I should mention that I stole a lot of the content in this slide from Alex Townsend, who gave a very good plenary a few weeks ago at ICOSM. So some of the pictures I just took from his slides, and with his permission, of course. Okay. So feel free to take a seat if you want. So in the last, let's say, 10 years or so, a lot of packages have sort of sprung up to vaguely address this question. So rather than having people who want to solve equations do everything by hand, provide an easy framework, a domain-specific language, a DSL, so that you can just, in theory, the sort of Platonic goal is that you can just write down an equation and say solve, and it will give you the answer. All right. Parallel to this is this other type of mentality, and this is more the Chebfun and the proxfun, is that due to MATLAB and more recently Julia and other packages, we've gotten very used to being able to manipulate matrices and vectors without really thinking about the details. What if we could do the same thing with functions? So there's these whole slew of packages in different languages, Chebfun and MATLAB, Daedalus, Firedrake, Phoenix, in Python, and also, well, nothing's in Python. Everything's in Python plus something else. And then approximation in Julia. I'm not going to say much about those. I'll say a little bit about these three. And what makes these three special is that they're all built on what's called spectral methods, or more specifically, Chebyshev-based spectral methods, which I'll explain a bit more later. Okay, so here's just the timeline. So Chebfun is a big MATLAB project coming from Oxford. I was not really involved with it, but I was around at the same time that other people were involved in it. My greatest contribution to Chebfun is if you look very closely at the logo, there's like a shadow. So I took their old logo that didn't have a shadow, opened it in Keynote, added shadow, copied it out, and that's my contribution to Chebfun. And mostly I didn't touch Chebfun because I didn't want to touch MATLAB, for the reason everyone here doesn't want to touch MATLAB. All right. Anyway, so later, a very similar Python package came up, Daedalus, and then I'll explain why I started working on approxfun, which was very much inspired by Chebfun. It's not, I wouldn't call it a Chebfun clone. The details are very different. But anyways. Okay. So why do we want easy-to-use tools? And you might think some people might think this is a ridiculous question, but it comes up a lot. So a lot of people look at Chebfun and these types of packages very skeptically because they think that numerics should be handwritten, fine-tuned code. But the reason why is often, so while industrial scale problems you might theoretically need to use hand-tuned code, there's a lot of very important problems on simple geometries. So on simple geometries, for these special classes of problems, it's nice to be able to just write down the equation and get the answer without thinking about it. Another reason, and I'll explain a little bit more about this, is that we want a teaching tool. We want to teach students how solutions to equations behave, how integrals behave, how derivatives behave. So having something easy to use is useful as a teaching tool. For me, the third one was my main motivation is that sometimes I want to do mathematical research and I don't want to worry about the details and I want to be able to just type things in. And the last one is that it's a good way of sort of selling numerical methods. So approximation sort of came up out of mathematical research that I wanted to prove, wanted to demonstrate was fast. Okay. So for the first point, here's, because everything in my talk is going to be very simple, I wanted to do a slide compiling all these things that are look complicated and fancy because I'm not going to be doing anything remotely like this, but just to show how this far this kind of idea can go. So the first one is a simulation in dataless of convection waves. And so you can sort of see the fairly complicated fluids. Here's some pictures of some PDEs on spheres, on disks. That one looks more impressive on the computer than it does here, but it's sort of a simulation in a ball, and so on. So you can see, while 10 years ago these talks were doing things on intervals, now they're sort of pushing things to start talking about serious problems. So even though the rest of this talk is mostly toy problems, I just wanted to make the point that you can push these kinds of ideas a lot further. Okay. So teaching tool. Oh, it didn't. So here's I just did a first-year undergrad poster project, and I did it using Chepfun because they learned MATLAB. I didn't want to force them to learn a new language. It was a 2-week project, and just being able to write down equations meant in 2 weeks, first-year undergrad students who had just learned differential equations could really push things a lot further than you would, that I imagine possible. So here's one poster where they solved. Now, of course, this is just an ODE solver in the back end, but it's just because they could just write down an equation, they could write down, if they can write down one equation, they can write down 12 equations, they can write down however many equations it takes to model 8 planets plus Halley's Comet, and a first-year student in 2 weeks can prepare a poster that simulates the solar system. All right. Here's another one, a bit more on the mathematical end, where a student could use numerics to understand the inverted pendulum. So this is something where if you take a pendulum and oscillate it up and down, it stabilizes it, which requires some bit of much beyond first-year mathematics of understanding stability of differential equations. But because everything they could just write it down, they could prepare this poster describing which regions an inverted pendulum is stable. They might not understand the full details of Matthew equations and mathematics, but just making things easy means students can go a lot further than well, I don't know what I was doing when I was a first-year undergrad, but I definitely wasn't doing stability analysis of an inverted pendulum, that's for sure. Okay. All right, here's one more example. This is from a lecture course I give here, well, in Imperial. It's a third-year mathematical physics course, and essentially, so this is, what is this? So imagine a plate, and here a plate is really a line, and a potential charge, and the plate is sort of has a fixed charge on it. This is a very simple to say physical problem, which takes, to write down the exact answer takes quite a bit of mathematics, but building on this sort of framework and principle of write down the equation, you can solve it. We can take a simple statement of the mathematics and convert it into a few lines of code and plot it, and do this as a way to demonstrate what's going on without having to do the full derivation of the exact formula. So this is sort of the motivation. It's not necessary, at this point, it's not necessary to compete with the serious simulations, but in theory we might eventually get there, but it's just, it's useful to have these types of tools around. Okay, so that's why Chepfun, why Daedalus, why these types of software projects, why approximation in Julia? Well, the short answer is I had a paper in 2013 where I said general linear differential equations can be recast. For those who are in Chris's talk, it sort of vaguely came up there. You can reduce differential equations to linear systems, and these linear systems had a very special structure of being banded plus 1 or 2 dense rows, 1 or 2 or 3. And so then in the paper we said you can solve this in O of n. I wanted a plot of O of n complexity, which means for n unknowns it takes less than or equal to c times n time. I wanted a plot of, I said it's O of n, I want a plot where the time goes straight up like a straight line. And so I had to do this all in sort of handwritten C++ code. Took a lot of time, was very unmaintainable, and when Julia sort of came around and I realized that I could do this all in Julia because it supports fast algorithms on special data types such as structured matrices. I could implement this in Julia without having to do things low level, And it worked. And actually, the Julia code is faster than the old C++ code that I wrote, which is more of a statement of me being bad at writing C++. But a consequence of this, which I'll show in the second part of the talk, is that because I had rewritten this all in Julia, I get for free a lot of features that would have been very difficult to do in any other language, maybe impossible. I get support for dual numbers, support for big floats, support for intervals, and so on. So that's sort of the reason why roughly I got interested in Julia, and roughly I got interested in developing approximation. All right, so one last slide before we get into the demonstration. So approximation is really sort of builds on a family of packages. It builds on top of Mikhail's fast transform code. It builds on top of Alex's fast Gauss quadrature code. It builds on top of these packages, which I wrote to handle special matrix types, such as block-banded and banded matrices. And then there's other packages that build on top of it. So it's more of like a family of packages than just one. All right, so that's the overview. And now let me switch to, let me see how well this goes. So the first question is, has the kernel crash? Because whenever I give a talk, I always want to do a live demo. The kernel always crashes, which means that instead of being able to hide the compile time, it's sort of there for everybody to see just how bad the compile time actually is. But I think in this case, luckily this audience, everyone would be understanding. Okay. So I just wanted to give a brief overview of what you can do with approximation and some of the features, and then dig a little bit into how everything is implemented. So the first part is the most simple one, is manipulating functions. So what this is showing is, first, I can create a function, in this case, let's say x, and what it's done is behind the scenes, I'll go dig into the details later, but it's created a special type called fun. It's storing some information about this function so that it knows how to recover it, and therefore we can override the different operations to sort of play around with these functions without worrying about the details. So here I made a function sine x squared, which, so what does that mean? That means I can, for example, evaluate it, and at a point, it's very close to being equal to sine x squared. Okay. It's not just storing the anonymous function, it's doing something more complicated than that, of course. All right, you can do cos x, you can add two funds, and then finally you can say differentiate it, and I've overloaded tick to mean differentiate. Okay. And you could differentiate it twice, or add f, or do, and so on. Okay. So that's differentiation. Another example is integration. So here I've plotted h and the indefinite integral of h, which is, this is sort of an anachronism, but I've overloaded cum sum h to mean the indefinite integral of h. So we can see it matches our intuition. When the function is positive, the integral is growing. When the function is negative, the integral is going down. Okay. Similarly, sum, so if I wanted, instead of the indefinite integral, I wanted the definite integral, that's sum. Okay, and now what's interesting is, let me just do, is that this whole thing, even though it's done in working with general functions, it stores around the general function, we can further manipulate it, is actually, what's that? So it's comparable in speed. So creating this function via this whole framework is comparable in speed to traditional algorithms like quad GK. So for a smooth function, we're not actually giving much up by doing things more generally. we're actually competing against the traditional packages. Even more, because it's done in Julia, we can also do, for example, big float. So here is an integral of some function which is calculated with big floats in a fraction of a second. And I wanted to do a comparison with quad GK, but I got bored waiting after maybe a minute or so. Okay, so one of the emphases is that we want to manipulate functions, but we also want it to be fast. And we want it to work with general types, which is what we get for almost for free because we do this in Julia.
And you know how accurate the result is?
Not rigorously. I mean, that's a question for you, I guess. But all right.
Okay, but you have some understanding of how.
Yeah, there's a heuristic algorithm. I'll get to the details before, but it's built on transforms. It adaptively grows the discretization size, transforms it, looks for decay in the coefficients, and then does a sanity check by checking at a random point. Now, that's not rigorous, but it's.
So how many decimal places do you expect to be right there?
So it does this based on epsilon of the precision. So for float 64, you get roughly 15 digits for something like this. It all depends on how many points you actually use, but roughly 15. This would just be epsilon, a big float, so it would be very, very accurate.
What if you just set precision for 2? So basically, all of those digits are correct, is what you're saying?
Well, no, I'm not saying they're all correct. I'm saying that they're on the order of, let's say,
Okay, almost all, let's say.
it's on the order of the number of coefficients times eps of big float. There seems to be a minus sign. I'm pretty sure eps of big float is not e to the 10 to the 74, but yeah, it must be. Well, oh, there was a minus sign missing. Okay. So I would say, I mean, I don't want to try to verify it right now because we'll see that it's completely wrong. But in principle, it should be that, roughly that accurate. Okay. And then if I did set precision higher, it would increase the accuracy. Okay. Later I'll do an example where I compare. So what else do you want to do with functions? You want to differentiate them, you want to integrate them, you want to add them, you want to algebraically manipulate them. You also want to do root finding. And it turns out that there's very nice algorithms for doing root finding with the way we represent these functions. Doing global root finding, finding all the roots. So here's a fairly complicated function. I've calculated all the roots by calling roots of the function. I've calculated all the extrema by finding the roots of the derivative. I've plotted it on top, and we see that it looks right. Okay. So that's smooth function, but we can also do functions with singularities. So here's a simple case of a singularity, which is a jump singularity. So I've created a function sine 20x squared. I've taken its sign. So this is a piecewise constant function, but it's sort of supported in this sort of language. Or here's something more complicated, which is absolute value of sine to the 0.3. Oh, this one was fun. This is something that blows up, but I can calculate both the function and its consum, and we can see here's a function with blow up. It has a piecewise singularities, and surprisingly, this works. At least surprising to me. And we can see that the sum of the function is whatever it is. Okay, so this way of working with functions is fairly general. We can push things pretty far. We can also do 2D functions. So here's just a simple function on a rectangle. And again, we can do integration. We can add them. We can calculate its integral. We can also do partial derivatives. So this is d dx applied to that function. this is plotting issues, but yeah, it is what it is. Plot, everything in Julia is plotting issues. Yeah. All right. Okay, and then just to sort of show this is the state of the art, which isn't maybe not that far, but it shows that we can push things beyond simple cases. This is doing function approximation on a triangle. So this is going beyond, squares are pretty easy because it's a Cartesian product of two simple geometries. Here we're doing something a bit more complicated. Okay. Okay, and again, we can do partial derivatives of function on these sort of specialized geometries. So that's sort of manipulating functions. That was sort of the first part. The second part was solving differential equations. And here we want to be able to solve differential equations as easy as writing down the equation. So for example, here is a very simple second order differential equation. I want it to be 1 at minus 1, 2 at 1, and this is a singularly perturbed problem. And we can just essentially just write down the differential equation, and behind the scenes it'll solve it using that sort of structured linear algebra that I mentioned at the introduction. So here, Dirichlet is code for evaluating on the left and the right, so that's why it's 1, 2 there, and B is Dirichlet. So here is a simple example, and because everything is done fast with customized linear algebra implemented in Julia, this is actually calculating the solution on the fly. Okay. So this equation is fun because it's, well, I was talked by Leslie Greengard maybe 10 years ago, and he mentioned this equation and mentioned how this equation is impossible to solve numerically because it has a condition number of 10 to the whatever 14 in an L2 sense. So it's kind of fun that we're able to solve it both fast and also very, very accurate, even though it's impossible. But it's only impossible if you talk about the L2 sense anyways. So that's a linear differential equation. What about nonlinear? Well, there's some basic support for nonlinear equation built up on automatic differentiation, but sort of a operator valued automatic differentiation. So we build up an operator tree using automatic differentiation so that a user can just plug in a simple, that's kind of hard to read, but simple, this is essentially a root finding problem. Find u that's equal to c at minus 1 and 0 at 1. Oh, I didn't do that right. C at minus 1, 0 at 1. And then solves this differential equation. And essentially what's going on behind the scenes is it's doing Newton. If you can do linear, you can do nonlinear via Newton iteration. That's a hand-wavy statement, but it's true. And we can see that it's, even though it's nonlinear, it's fast enough that we can solve the equation on the fly. Okay. Okay, finally, to really show off the power of having done this all in Julia and also having done the linear algebra implemented in Julia rather than relying on, say, UmpPack or other packages that are targeted at special types, is that I can plug in, say, a special type. Here it's interval arithmetic with big floats and backslash. So here I'm writing down the equation. Let's see if I can translate this equation. This equation is u of 0 equals 1, u prime minus u is equal to 0. And then I evaluate this at 1. I'm sure many people know the answer. It's just E. So here I'm giving the computer just the definition of the differential equation. Say solve the ODE, solve it with interval arithmetic, but I've actually not approximated anything yet, because 1 is on a computer is 1, big float of 1 is 1, interval of 1 is 1. behind the scenes it does backslash with interval arithmetic. I get that for free because all the operations are overloaded with, this is using David's validated numerics package. And then I get an interval out saying that E lies between these 2 points to 1,000 digits. Now this isn't actually rigorous, but in this case it worked, and we can verify it with x of a big float of 1 and see that, yes, I've gotten an interval that contains big float evaluated with set precision 3,000 up to 300 digits. Okay. And this was, let me just run it because it's actually really quick. Otherwise it looks like actually it's even quicker than I thought it was going to be quick. I thought it was going to be quick, it was even quicker than that. I mean, maybe this isn't that quick compared to non-interval arithmetic with non-big floats, but it's still pretty nice that you can do these general things using the same language. Okay, so that's the, you can also do this with dual numbers. Maybe I'll skip this. So here's like an optimization problem where I want to find an interval, and I just made that interval a dual number, use that to calculate derivatives of, so this involves a lot of things, including solving an ODE. It's done all with dual numbers, so we can calculate derivatives in a sense for free, and therefore do a simple Newton iteration to find the interval that solves our nonlinear problem. Okay. So you get a lot of flexibility out of having built everything in Julia, which simply it's, if you say you can do this in another language, I don't believe you. Okay. Okay, so that's ordinary differential equations. This whole framework carries over to partial differential equations. So here's some simple made-up example. I create the domain, which is the product of two intervals. I say I want Dirichlet conditions, and I want it to equal f. In this case, I just took f equal to 1. This is a simple Helmholtz equation. Again, we can solve partial differential equations essentially as easy as ordinary differential equations, though maybe not as fast. All right. Okay. And this also works on the triangle and so on. So that's sort of an overview of what, oh, it jumped, what we can do with this kind of technology. And so, again, it's still a toy. One triangle is a toy. But when I started working on this stuff, and when Chepfon started, it was a single interval, then it was a square, and then it was a triangle. And then also Chepfon works with spheres now. So it started off as even more of a toy than it is now, but I think the long run is if you can do one triangle, then you can do multiple triangles, then you can do multiple tetrahedra, and then you can start talking about serious problems. But we're a lot closer to where it was 10 years ago. Okay. So that's the overview of what kind of things you can do with approximation. Now I wanted to dig a little into the actual implementation details. So what's the basic idea? So the basic idea underlying it is something that we're all familiar from sort of first year mathematics, which is that functions are continuous functions can be thought of as infinite dimensional vectors. So one way we do this is Taylor series. So we all know, or I hope we all know. If you don't know the Taylor series of e to the z, maybe this is not the right workshop for you. At least I know. I know the Taylor series of e to the z is 1 plus z squared over 2 plus z cubed over 3 factorial and so on, which we can write it in this sort of vector notation, that this function, well, 1 over n factorial decays very, very quickly, so this function is equivalent to an infinite vector where we interpret the coefficients of that vector as being coefficients in this basis, and because it decays, we can truncate it and therefore represent the function e to the z by a finite dimensional vector. Okay. So how does this work in approximation, well, what it does is it takes an anonymous function. It doesn't know anything about x plus z. All it knows is that it can evaluate it point-wise, but that's enough that it can, so the real is just to get rid of complex noise. It's actually doing this on the circle in the complex plane, but let's ignore that. So it uses that information to adaptively find that this function e to the z can be represented by 18 coefficients. And it knows how to interpret those coefficients because there's a second field space that says these are Taylor coefficients. Okay, so a function is a vector, a finite vector, which is code for an infinite vector padded with an infinite number of zeros, and a space, which is how we interpret those coefficients, a basis to interpret those coefficients. Okay. So how does it determine the coefficients? Well, as for those that were in Chris's talk, what happens is it sort of adaptively tries evaluating it on a grid and performing a transform. So in the case of Taylor, this is just the FFT actually. So it evaluates at a grid of points, in this case in the complex plane, of 20 points, and applies the transform to those points, and then it sees that it sees decay. Probably it's converged. If it hasn't seen that decay, it would increase the number of points until we see decay, or it would eventually reach 1 million or so points and give up, but that's another issue. So it adaptively increases the grid, does a transform, checks for decay, and then does a sanity check to make sure that f at some random point is approximately x at some random point. Okay, so that's what goes on behind the scenes with Taylor, but it turns out this basic idea of grids, transforms, decaying coefficients works for way beyond just the case of Taylor and Fourier. So another example, which again Chris mentioned, is it's time to pick up my daughter from nursery. Is the Chebyshev expansion. So the Chebyshev expansion is expansion in tk of x, which is just cos k or cos x. This is actually cosine expansion in disguise. And for smooth functions, it has the same sort of convergence properties that Taylor series does, where if a function is smooth, it has very rapidly decaying coefficients. Therefore, we can evaluate it on, it's a different grid, it's called the Chebyshev grid. We can evaluate it at 20 points, check the coefficients, see if there's decay, evaluate it at 40, and so on, until we see convergence, check at a random point, and it works incredibly reliably. So this can be, in a sense, anything within reason that's smooth. Okay, so well, eventually it takes a while. Okay, I got carried away. All right, let's hope the kernel didn't crash. I don't know why. That shouldn't have. Oh, it's the at show. Should I just restart the kernel now and hope for... I think I don't want to wait for it to print. All right, let me restart and... All right. Okay, I'll start that. We'll see how that goes. I think I need some other things. I don't know. All right. Okay, so while that compiles. So luckily I've pre-done most of the cells, so shouldn't be an issue. So then you could do this with other bases, Fourier and so on. Or we can really push it. Here's sort of, so what does this mean? This means Jacobi weight is weighting by 1 minus x. Well, this is just square root 1 minus x squared times Chebyshev. So I'm actually incorporating singularities into the function. I'm taking a product of two spaces to make a space on a rectangle. Again, all it knows about the function is how to evaluate it pointwise. But because I've told it what the singularities are, it can sort of compose these grids and points and transforms in a way that I can do sort of general functions like this and have it work automatically using the exact same construction process. Evaluate a grid, evaluate the function of the grid, transform it, check the coefficients, check at a random point. Okay. And I could make these, one of these Fourier, let's say, and do Fourier times Chebyshev just as easy as
What's the checking at the random point called?
aliasing. So with FFTs, there's this problem of aliasing is that one looks exactly like cos 100x if you take your grid wrong. So it's not enough to just check the coefficients. You also, because you need to be able to tell the difference between 1 and cos, well, it depends on your grid, but so the random point is a way to get around that.
Would that be assuming the function's periodic in Y?
Yeah, so if I change this to Fourier, that means, well, in this case it is, oh. So, okay. Now we have to wait for the compile, but you can see here I was able to construct this square root weighted Chebyshev polynomial basis in X and compose it with Fourier in Y, and because things are done in sort of a generic fashion, it works. Okay. So what else do I want to say?
Could the package handle discontinuities in a region, not just points?
You mean in 2D or?
Yeah.
You would have to have a space that incorporates those singularities. So I wouldn't know. So that's the sort of case where you're back to, without coming up with something new, you're back to the regime where you want to go back to sort of adaptive grid refinement. Okay. All right, so what else do I want to say? Well, if, I'll just keep this brief, I think. If functions are vectors, what are operators? What are operators like multiplying by z? What are operators like derivative? Well, if functions are vectors, operators are just matrices. So, for example, to differentiate a Taylor expansion, we just shift everything up by 1 and multiply it by k. So that gives us this infinite dimensional matrix with 1, 2, 3 on the off diagonal. Or for Fourier, the derivative is something else. This is all represented in a prox fund by these lazy data structures that know how to populate themselves and also know the structure. So this knows that it's banded, and that's why there's dots and non-zeros there. It doesn't know it's as banded as it actually is, but it knows it's banded at least. Okay. You can also do, so a function is always a coefficient and a space. You can do an operator that takes coefficients in one space and gives coefficients in another space. So for example, if I have a function expanded in cosines, its derivative is, you would want to expand in sine, so therefore the derivative operator acting on an expansion in cosines gives as an output sines. And so this is sort of the basis of the Chebyshev type methods, is that it has the same principle that if we change the coefficients, we can get banded operators for representing derivatives. And this is how we get to our sort of structured linear algebra, which was the whole point of doing everything in Julia in the first place. So I think I'll just gloss over it, but I'll say if we have a general differential equation like this, we can put it together in an operator. This is an operator from a Chebyshev function to an array of 3 different spaces, however it interprets those coefficients, one corresponding to the value at -1, one corresponding to the value at 1, and one corresponding to the range of the derivative operator. And this is all done in a way so that if I take a finite truncation of this matrix, I have a very structured matrix, which this is what I call an almost banded matrix. So banded matrix plus 2 dense rows. And then this special data structure feeds into the banded matrices package. So, which has optimized O of n algorithms in place. Okay. So finally, what else do I want to say? I think I'm at the end of my time. So we can. Oh, well, that was our next speaker, so I guess I have plenty of time. All right. So we can represent operators as these very structured matrices. Then we can do linear algebra. One example, which is particularly important because it's robust to conditioning, is QR. And essentially what we can do is do this all adaptively, because these are stored as lazy infinite dimensional matrices. We can do linear algebra on sort of the structure adaptively. So here's an example of taking that banded matrix with the 2 rows. When I do backslash, it does QR. It adaptively does QR on column by column until it sees convergence. And we can see why this works is because, so here I've done it explicitly and said do 20 iterations of QR. That means it's upper triangularized the first 20 columns. Now, this looks like it's created fill-in, but what we see is that this special structure is preserved. So, all right. Well, I guess the speaker is back. So we see that this fill-in, it looks like it's a dense matrix, but it's actually still rank 2, just like the original thing. Okay. Anyways, this translates into partial differential operators. It's not banded, now it's what's called block banded, but we can see that we still have sparse structure and that we have control over everything here. And so that's how you can sort of ramp this up to partial differential equations. All right, so let me just finish off by saying where does the future lie? Well, we can do 2D. Hopefully we'll eventually be able to do 3D. We can do one triangle. Hopefully eventually we'll be able to do many triangles and many tetrahedra. We have to answer this question that was raised during Chris' talks of how do we parallelize things, but I think we have a plan of parallelizing on the level of linear algebra. And then finally there's some fun stuff going on there, but I don't think I want to say anything about that. Okay. All right, I'll stop there.
So is there a vision for like time-dependent PDEs and adaptive?
Yeah. So the
is adaptive. Sorry, I just get a sub-question. Is the main purpose of this package the adaptiveness, the geared towards refining, having very
so essentially what it does is it gives you spatial additivity for free, and then you say, okay, then you plug that into differential equations.jl, and then you get time and spatial additivity for free. It's more complicated than that because of it. If you don't have an L-stable scheme, you can get sort of plateau effects which sort of destroy the additivity. So in theory, it's doable, but there's still some thought that needs to be done to make it truly adaptive. So That's why in Chris's talk, he sort of didn't use any additivity. He did everything on finite dimensions because of these issues. But yeah, but that would be the goal. All right, so are you ready? Do you need this, or you have your?
No.
Oh, yeah.
Can you hear me? Should I start? Okay. Hi, everybody. I'm going to talk about what we could call validated numerics, or verified numerics, or rigorous, or guaranteed. It has different names. So this is some work that I've been doing for the last 4 years or so, together with Luis Bernet, my colleague from the National University of Mexico. And basically, this package originated when we discovered Julia at the start of 2014. And so we've been developing this in tandem with our growing understanding of Julia and the growing of Julia itself. And so it's basically been rewritten several times. And so actually, over the last year, this suite of packages has expanded quite a lot, and the performance has improved drastically. And so I'll talk about a few of those things. So what am I going to talk about? I'm going to talk about this suite of packages that lives in the Julia intervals organization. And so that suite of packages is a set of tools based on something called interval analysis or interval arithmetic. And it's a set of tools that do set computation. That means computing with sets of real numbers. In particular, intervals. Everything's based around intervals. So we're going to calculate with an interval which is all the real numbers, say, between 3 and 4. We're not just going to think of them, we'll think of them as sets, but we'll actually do arithmetic and other functions, mathematical functions on intervals. So it's definitely related to approximation kind of thinking. It's a bit different. We'll see some of the similarities and some of the differences. And so recently there's been some interest from various new collaborators, which we're very excited to see. And also we had a Google Summer of Code student, Ishan Gupta, who was working on various, couple of the packages. And these packages are now being used in other places in the Julia world, in particular Ego, which is a much more complete global optimization package, and the Julia Reach organization for reachability analysis for dynamical systems, neither of which, of course, I'll talk about. And we have a talk on Friday, which is something like a blending of today's talk with something closer to approximation, when we'll show how to use these ideas to bound functions rigorously and solve ordinary differential equations with that kind of idea in a rigorous way. Okay, so I'm going to start off by showing some problems that would traditionally be thought of as being difficult in terms of root finding and optimization. So we just saw some nice root finding, and I'll show some more. And then after showing what the packages can do, I'll go into how the underlying mathematics works in terms of how to do this interval arithmetic, and I'll talk about how to handle constraints and some algorithms that we actually use. So all of this is available, almost all of it. I realize that not quite all of it is now available with this package called Validated Numerics. But actually that package is now just a sort of wrapper, a meta package that pulls in all the individual packages that I'll be talking about. So, but if you do using Validated Numerics, you'll get most of this just available to use. Okay, so let's look at some difficult problems. So Suppose we have this equation, this inequality, sine of y times x of x minus 1 is less than 0.5. What set does this inequality describe? So this is, some, could be inside some optimization problem. So this is part of the so-called feasible set, which is just the set of solutions, the set of points that satisfy the constraints in some optimization problem. But without even going to the optimization problem, we can ask, well, what is the shape of that set? So how would you do that in Julia? So probably what you would do is draw a grid and sample from the grid and draw a point in one color if it satisfied that, and in another color if it didn't. And we're going to sort of do that in a rather more sophisticated way. And so, so I actually ran all the code just before the talk to make sure. So I'm not going to do exactly a live demonstration because I've had issues with that before. But it is live in the sense that I just ran all the code and it all works 5 minutes ago, kind of thing. So I don't really want to, and also some of it takes a bit long to do it as a live demo. Let's hope that it all works. Okay, so, oh, you can't really see it that well. You can sort of see it. So, so what are we seeing here? So so the packages that I'm going to be using are these ones that all begin with the word interval. So there's interval arithmetic is the basic one. That provides the basic underlying arithmetic on intervals that I'll talk about later. And then built on top of that, we have a package for finding roots of functions, a package for global optimization of functions, and a package for so-called constraint propagation. And so I'm going to start off with a constraint propagation, just simply because it's something that I never managed to reach in any of my other JuliaCon talks. I never get there, so I'm going to start with that by showing that today. And so what are we doing here? So here's my function, sine of yx minus 1, and I've got this constant a, which I'm actually going to change with and manipulate up here. I can put that inside my constraint. So this at constraint is not the same as jumps at constraint. This was developed independently, but part of the future plans is combining, being able to use our packages from within jump. But so this at constraint actually creates a new kind of Julia object called a separator. And basically what that does is it takes a box and contracts it by excluding from that box portions of the box which are guaranteed not to be in the set that's described by the constraint. So I'll talk about how to do that later. This second line, x equals this thing, so this times operator is actually, so this minus 5 dot dot 5 creates an interval from minus 5 to 5. Then the times creates a so-called interval box. So that's basically a Cartesian product of an interval in x with an interval in y, so that makes a box in the plane. That's my basic box that I'm going to work inside. And then, so I take this whatever kind of contractor object and the box, and I do something called a paving. So what that does is this more sophisticated version of the grid and coloring the grid according to whether the point is inside or outside the set described by the constraint. So when I do all that, we have a plot recipe, so you can just plot these objects, and we get this result. So hopefully you can see that there are some blue regions and some red regions. Apologies, I shouldn't have chosen blue and red. It's not a good combination for some people. And some white regions. So the white regions have been guaranteed to be excluded. So they are definitely not in the set described by that constraint. The blue ones are definitely inside that set, and the red ones, we don't know. And if I were to change this 0.1, this tolerance, this precision, that's basically the box size, if I were to change that, then I would start refining this region. I can actually get a more precise answer about whether these points, which we don't yet know whether they're inside or outside, whether they're inside or outside. And if I have a manipulate, if we're lucky, I should be able to change that, and the figure should actually change interactively. There we go. Okay, so it's not quite as fast as Sheehan stuff, but it's pretty fast. And so, so we can actually, do what you would, yeah. So the point is, okay, So the point is you can do this in, say, Mathematica, but this picture is actually a guaranteed to be correct, if you believe that the software works, right? It's guaranteed that the blue region is inside this set defined by this constraint, and it's guaranteed that the white set is outside, and the red set we don't know, but we could refine it further. Okay, so that's a claim I'm making, and then I have to show how we could actually make those guarantees later on.
Before we move on,
Yeah.
is there any problem with rounding errors for the value of A? So it's guaranteed up to the closing point.
Okay, so yeah, so the question was, is there any problem with the rounding errors in the value of A? And so I would say that the answer is taking, it's probably what it's doing is taking the exact floating point number that I've put in, rather than the exact real number. And if I were more careful, I would want to put in an interval instead, but I'm not sure if I can do that in the current version of the software. Good, thanks. Okay, so here's another example that comes from a paper by Tupper. What is the set in the plane satisfied by this complicated inequality? In these 5 lines, in, I don't remember how long it takes, like 1 second, I can characterize, with some precision, okay, it's a bit more than 1 second. This is, again, with the same color code, this is the set, and I can just change this, this tolerance. It'll take longer in some, I think it scales linearly in 2 dimensions, and I get a better approximation. So when I first did this in Mathematica, Mathematica actually had an extra bulge where there wasn't one. Now they seem to have improved it, but because this is a guaranteed picture and theirs isn't, right?
Have you benchmarked it against
I haven't.
more seriously?
I have not done serious benchmarks of any of this stuff yet. Yeah, I'd like to do that. Okay, so there's a great package called nlsolve.jl. Okay, so that was, constraint satisfaction. What is the shape of the feasible set? Now let's move to finding roots of equations. So there's a great package called nlsolve.jl that has a pure Julia root finder for n-dimensional systems of nonlinear equations. Here's an example from their README. There's two equations. One is a polynomial and the other is not. So can we find the roots, x and y, that satisfy these equations? So they show how to find one root, right? So let's draw this thing. So this is just one of those. This is the sine one. This is what it looks like, and that plane is cutting at 0. There's probably can't see it very well, a shadow plane that cuts at 0, and so we get some really complicated set that we can draw using standard Julia contour plots like that. And so these are the two equations that we're trying to solve simultaneously, and so we're trying to find the intersections of those two things, right? One is this blue curve that goes like that, and the other is this set of red curves. And so any intersection of those will be roots of this equation, and there's going to be an arbitrary number of them as we go further and further away. And so they show in the NLSolve documentation that you can start somewhere here, and it will sort of do some I don't even know exactly what it does, one of the standard optimization methods, some kind of gradient-based thing, and it will converge to one of the roots. But then how do I know? And then if you start somewhere else, it might converge to that root or might converge to a different root. So how do I know if I found all the roots? The answer is I don't. I can never know with the standard methods if I found a root, they might not converge at all. So what can we do? So now this is how does it draw these contours? It uses an algorithm, I believe, called marching squares, which is kind of similar to what we do, but there's no guarantee that this picture is correct. So now, using, again, constraint propagation, here is a correct version of that picture. So again, this is a guaranteed version of the picture. And so what I've done is set up these two constraint objects, which now have equality in. And I pave both of them. So I find the set of boxes, little boxes, that cover both of those sets. So one of them is this red stuff, and the other is this faint blue thing. And then what I did, if you look here, is I actually took the intersection of these two objects. Right? So these are two sets, but these sets actually correspond to, so this at constraint, as I said, is making this separator object, which is a function that I can apply to a box, and that tells me which piece of the box is inside and which piece is outside. And there's a way to take two of those separators and make the intersection object, which tells me whether the intersection of those two things is inside or outside. So that's what I'm doing. And so it's supposed to be, okay. So it turns out that it's actually much quicker to calculate the set that satisfies this intersection of these two constraints. Basically because I can throw away a whole lot of the space. As soon as I realize that a box is not in one or not in the other of these constraints, I can just throw it away. And so it's quite possible that it's throwing away huge swathes of territory, huge pieces of the search space. It just immediately realizes, no, that does not satisfy one of the constraints, and it gets rid of it. And so it's actually very fast to find this intersection set, which I plotted in black. And the roots must lie inside this new black set. I can also manipulate this, and I can manipulate that, and we see that it's, finding the new roots for each value of A.
To answer your previous question, how do you know you got all of them?
Yes. So how do I know I got all of them? So currently all I'm saying is that I know that the set of roots of this equation inside this initial box that I gave it, the set of roots is contained in this set that I just calculated. So now let me actually calculate the roots. Do I get a multiplicity? No. I'm just saying that the set of roots lies in there. So now I'm going to calculate all the roots, assuming no multiplicity. If I have multiple roots, that's actually not something that interval methods can tell you in principle exactly. So now what I'm going to do is use this other package, interval root finding. So this does not use this constraint propagation method yet. That's part of the work of Sheehan in Google Summer of Code that is going to be incorporated soon, hopefully. So what this is doing is, I'll talk about it a bit later, it's also doing basically bisecting the space and looking at each piece and trying to see if there's a root inside in a similar way. But then I use, in this particular case, so that would be a kind of bisection algorithm, and that tells me that tells me where there cannot be any roots. But now if I want to prove that there is a root inside some region, I use something called the interval Newton method, which is a version of the standard Newton method for finding roots, but designed specifically for intervals. And what this does is guarantees that if a certain condition is satisfied, it guarantees that there is a root in that interval box, in this case, and it is unique inside that box. So there's actually a rigorous way using floating point arithmetic to prove that there exists a unique root inside a box. And so when I run that on this particular problem, I get a list of 80 roots inside the box minus 10 to 10, and it has proved to its own satisfaction that, so this true is just running through and checking that all of these labels are unique. And that means that in each of these little tiny intervals, it has proved that there's a unique root. And so this statement is saying that there are precisely 80 roots of this system in this box. And this, in principle, works in n dimensions. In practice, of course, there's a curse of dimensionality. There's an exponential explosion when you bisect in n dimensions. And that's where the interval constraint propagation comes in. That should enable us to eliminate these vast regions of space, even in n dimensions. Okay, so let's look at another example of that. Let's calculate the stationary points of a complicated function. Here's the complicated function, and here are the stationary points calculated just by doing, here's the function. It's a function of two variables, x and y, some moderately complicated thing. And here's the call to roots of the gradient of f using forward automatic differentiation from the forward diff package. And so here are all of these stationary points are highlighted with little dots. Is that visible? Okay, and then what can I do? I can actually calculate the stability of each of those just by counting the number of eigenvalues that are bigger than 0 of the Hessian, again with forward diff. So here, this calculation is not rigorous. So the previous calculation was rigorous. This is proving that there are exactly 529 stationary points in this box of this function. And they are those. And they are unique in their little intervals. And now I'm doing a non-rigorous calculation to classify them as maxima, minima, and saddle points. And here they are in different colors, the maxima, the minima, and the saddle points. And I could actually make this rigorous if I want. I have a version that makes this rigorous, where you rigorously prove this is a maximum, this is a minimum, and this is a saddle point. Is that clear? Okay, so here's an example in, so 2 dimensions, kind of boring. How about 3 dimensions? So let's look at the famous Lorentz system, 3 differential equations that has a chaotic strange attractor for certain values of the parameters. So I'm going to use the differential equations.jl package to solve the equations in a non-rigorous way, but I'm going to find the fixed points of the equation using my interval root finding package. So I give it an initial big box. So let's just go back to the code. So here it is. I give it an initial box that's from minus 50 to 50, and it's 3-dimensional, so that's minus 50 to 50 in x, in y, and in z. And then I just say find the roots of this function that I define, which is the Lorentz system with its parameters p, over that box. And I take the midpoints in order to plot them. And so you can see the green dots here, hopefully. They are the fixed points that were calculated. So it's guaranteed that there are exactly 3 fixed points in this big box, and they are here. And then I can move this parameter value, and we see that there's this global bifurcation just here. So I could do this with Plotly.js. Maybe I should do that. Well, I'll just carry on and then I'll do it. So I can carry on, and then at some point there's global bifurcation to chaos. Right? And so this is the nice thing about the plots.jl package, is that I can just switch out the backend and choose a different backend using Plotly.js, and that enables me to actually rotate these things. The only downside is that it's not quite so smooth to change the values of the parameters, but I can see what's going on pretty nicely in 3 dimensions, etc. Right. Anyway, the point from the point of view of my talk is that in the case of the Lorentz system, you can actually calculate these 3 fixed points analytically, but I could just change the system now, and let's do that actually. I could change the system that I'm calculating, and even if they weren't analytically available, I could just immediately find all the fixed points in a guaranteed way. Okay, so the other pretty nice thing that intervals allow you to do is global optimization of functions. So here's a kind of nasty function called the Grievank function from Rn to R. So it takes a vector, and it calculates the norm of the vector divided by 4,000, and this product of weird cosines of x divided by the square root of I. And so we can easily write that in Julia. So I should say that apart from the constraint propagation, all of these packages, and the constraint propagation is now also going in that direction, all of these packages just take standard Julia functions. This is just a standard Julia function with no macros, no nothing. Right? I'm just defining this thing on assuming that x is a vector. I define it with standard Julia code. That's what it looks like, the 2-dimensional version. So it's another one of these functions which are super spiky. And so this would be a nightmare for any local optimization code. It would just kind of get stuck in one of these local spiky minima. But if I want to find the global minimum, what do I do? Well, intervals can do that for you. And so here I'm using the interval optimization package. And what that does is has a function minimize. You feed it a Julia function, you feed it a box, and it returns a guaranteed bound on the global minimum, the value of the global minimum, and a guaranteed collection of boxes that contain the places where that global minimum is attained. And so here, I'm just have a slider where I'm changing the dimensionality of the problem, right? So I'm changing the number of entries in this vector that I'm optimizing. And so you can see that it's taking longer and longer each time I move this dimension, but actually that's also including the compilation time. If I go back to the previous value on the slider, it's super fast. So it's optimizing, a 5-dimensional function in some small number of seconds. I can actually just jump up to something like 50 dimensions, and it'll take a while, but there is the global optimization of this function, in 43 dimensions in a couple of seconds. So this is something like 10 times faster than the equivalent package in MATLAB, apparently. Okay, so as I maybe mentioned, we're hoping to incorporate this as a subroutine in JUMP. So I was talking to Juan Pablo and his student Chris Coe recently, and basically they were saying that it's often very useful in big, difficult optimization problems to have something like this as a sort of small subroutine that can work as a part of those big global optimization problems. So even though this just is going to work in some low number of dimensions. Okay, so and then finally in this part, what about constrained global optimization? So can we minimize x plus y such that x squared plus y squared is less than or equal to 1? So that looks like this. I'm changing the so that x squared plus y squared less than or equal to 1 means I have to be inside the disk, and so I'm drawing the straight line is x plus y equals a constant a, and I'm changing the value of a, so we can see that the minimum value of a that's possible, it's not doing anything, is over here. It's minus 1.4, minus the square root of 2, and we can now do that with our package. This was the work of Sheehan and Google Summer of Code, so we can minimize, using interval constraint propagation, the constrained problem of that function over that box, which is actually an infinite box. So some of these functions work over infinite boxes. So we're finding the guaranteed global minimum of a function on the plane, and proving that its global minimum is within that box. And here is a list of small boxes that the union of which contain all the places where this function attains its minimum. So the fact that this is a collection of small boxes is something called the cluster effect, and it's a problem in these methods. And there are various possible avenues that we can explore to reduce that effect.
How does this one work? Finds the KVD conditions for the...
No, so this is...
Or it's actually optimizing?
This is, so the question was, how does this work? And so I'll talk about that later. When do I need to stop? Okay, so how does all this work? So it uses interval arithmetic, which means we're going to calculate with sets. What does that mean? So an interval is just a collection of all real numbers between a and b, and we want to define arithmetic and other mathematical operations on an interval. And the way we're going to define it is we're going to define an operation, for example, take the square of an interval, just to mean take the square of all the numbers in the interval and give me back a new interval, right? So if I square an interval, I get a new interval. And for example, 1 to 2, that interval, this is an interval, not an array in Julia, right? This is the mathematical interval from 1 to 2. That squared will be take the square of all of the numbers between 1 and 2. So obviously I can't actually do that on a computer, one by one anyway, but I can do it by mathematically analyzing what the result should be, and the result should be, in this case I'll take the minimum value and I'll square that. I'll take the maximum value and square that, and that will give me the minimum and maximum of the new interval that results from that. But I have to be a bit careful, because if I have minus 1 to 2 squared, I can't just do what I just said, because this function is not monotone, and so I actually have to split it into the pieces which are monotone, and then it's easy to analyze the function. And so the result would be something like this. So you can easily write this in a computer, right? So you define an interval type in Julia and define square on that interval type by this formula. And then when you square any interval, it will give you a result which is going to contain all the possible squares of all the possible numbers in that interval. Similarly, for binary operations like plus, I'm going to define the sum of two sets to be the sum of all possible values in the first set with all possible values in the second set. And I can do that again with an operational definition in a pretty simple way. And so I have to go through all of the arithmetic and elementary functions and work out how to define those operations acting on intervals with this property, right? To guarantee this property that the result always contains all the results. And when I do that, when I combine then these functions, I get the fundamental theorem of interval arithmetic, which is that we're going to define this so-called natural interval extension by the idea, replace the value x, a number, replace that by an interval everywhere, and then use the corresponding interval operations. And when I do that, for any function f that I can decompose like this, then, which we're going to denote by f of the interval x, the theorem is that that is actually guaranteed to contain the true range of this function over the set, which is the set of f of x for all x in my set. So that's the basic idea of interval arithmetic. Right? So let's just take a moment to say that again. So interval arithmetic is a way to define mathematical operations on intervals with the goal that any operation that I do on an interval, that will give me back a new interval, and that new interval is guaranteed to contain the result of f of x for all x in my original set. Yes? Yes, it's not unique. That's a good question. Yeah, so the result is not unique in the sense that if I write my function f in a different way, I could get a different set out. But the result is, however I write it, it will always contain the true range. So some ways of rewriting it will give me a smaller, better approximation, and some will give me a big overestimate. And so that's one of the problems of interval arithmetic. I can get a result that's too big, that's an overestimate. But in any case, it will be guaranteed to contain the range. So why is this useful?
What about floating point rounding?
Yeah. So,
Are you safe on the...
so there's a very important issue about floating point rounding. So I'm doing these calculations with floating point numbers, and the answer is I have to make sure that when I do all of these operations, every operation, the lower endpoint of the interval has to be rounded down, and the upper endpoint has to be rounded up. And this is actually a big issue. And so within the last year, we completely changed how rounding is implemented. And that was lucky because the previous rounding type that we were using is deprecated in Julia 0.7 because it doesn't work very well on Windows. What does? Yeah.
So when that theorem was proved, it was probably proved on like mathematical theorems or on mathematical functions, right? But now we're talking, we're using Julia, and we're like, we have this idea of like differentiable programs, and we take this interval arithmetic type, and we put it into the adaptive ODE solver, we get out intervals on the other end.
Yeah.
Are we still able to apply that theorem and able to say that what comes out is rigorously proved to be within the intervals, or what happens at that point?
So the question was, what happens if you now have some complicated differentiable program and you stick intervals in? And the answer is, it will give you an interval out that is guaranteed to contain, f of x for all x in your initial set. But that is not the same as guaranteeing that your numerical method is, that the result is, if you have some ODE solver that does some approximate, like a Runge-Kutta thing, that does some approximate method, it will not give you a guaranteed result that is guaranteed to contain the true solution of the ODE. It's guaranteed to contain the true solution of the Runge-Kutta method on the initial interval that you put in. That's the answer. Yeah.
Is the interval, the more operations you do with intervals, presumably the size of the
Right.
interval grows, right?
Yeah, so the question is, does the size of the resulting interval grow as you do more operations? And the answer is yes. And so this is something that you have to worry about. I was discussing this with Sheehan earlier, and he said, well, just use big floats.
Well, I guess what I'm imagining, so for instance, like a practical case in my world is if you want to align two images, there are only a few, like if you're going to rotate, translate that in 2 dimensions, that's only 3 parameters, right? But if you want to actually see how well they line up, that's a million computations.
Right.
Comparing pixels, right?
Yeah, so I'm not saying that interval arithmetic is a panacea that will magically fix any floating point computation. People said that in the 70s, and that's why other people stopped using interval arithmetic. So what I'm saying is interval arithmetic provides us with the foundation for some algorithms that are super useful, even if you don't use interval arithmetic, like finding all the roots of an equation in a guaranteed way, or doing these set computations.
So you rely on a certain set of primitive operations.
Yeah.
by intervals.
Yeah.
I vaguely remember that there was talk about future hardware platforms that might support some of that.
Right.
better than-
Yeah, there were various attempts, I guess, to do interval arithmetic in hardware. They seem to have mainly failed, but modern GPUs do have plus with directed rounding, for example, built in as elementary operations, unlike Intel CPUs where you have to change a global rounding mode, which is really nasty, and that's why we changed the way we do in rounding in the package. So there's interval arithmetic package, provides these interval types with these operations. There's a huge test suite that didn't originate with us. There's a test suite to check compliance with an interval arithmetic standard, IEEE standard that came out a few years ago, and currently, and the package passes all of the tests that we have integrated so far. So that's a good guarantee that it works. So how do I make an interval? I use this dot dot notation. So 3 dot dot 4 makes the interval from 3 to 4. And it has this type, interval, and it's parameterized on the type of floating point number that lives inside. So the same code works with big floats, would work with all kinds of other weird floating point types that people have defined, except that we have this requirement on directed rounding, which means that we can't really use any floating point type that people have defined. So, so now if I do x squared, it knows what to do because, as I said, we overloaded the operations in the way that I was talking about. And so now if we just define a standard Julia function f of x, which is x squared minus 2, and I put in my interval, it will do first the squaring operation, then it will subtract 2 from all of those results, and it will give me a new interval, and that interval is guaranteed to contain, this is all done with rounded floating point arithmetic, it gives me a result that is guaranteed to contain the range of my function f over all the real numbers in my set x. And in particular, well, this does not contain 0, right? 0 is not in this set. And I can check that using the in operator in Julia. And so we've used floating point arithmetic, but we have a theorem that came out of that in 3 lines that f has no root in this interval. And in fact, I can take this interval that was 3 to 4 and replace it with 3 to infinity. So infinity in Julia is a number. It's not really a number, it's a special thing in IEEE floating point arithmetic, which is taken account of by the package. And so what can I do? I can stick in this semi-infinite interval. I get out a new semi-infinite interval. And what I've just proved is that there is no root of my function in that semi-infinite interval. Right? So that's what I mean by we can exclude a huge region of search space. I'm looking for roots of this function. I just excluded an infinite region from my search. So that's why these methods are unique. These interval methods can do this kind of thing where they operate on a whole set at once. And that's why they're set computations. Okay, so I can compose them with other packages, compose interval arithmetic. For example, forward diff, I want to calculate the derivative of this function over that interval. What does that mean? It means bound the derivative of the function over that interval. In other words, I want an interval that is guaranteed to contain all the derivatives at all points x inside that interval, and it just works. So the forward diff authors knew nothing about interval arithmetic. We knew almost nothing about automatic differentiation, and because it's Julia, it just works. And then what we can do is, for example, the Jacobian of a function from R2 to R2 with a big interval and then take the inverse of it, and it all just works once you've defined a couple of extra functions. I mean, like, is inf, like so this is delicate, actually. So we actually had an issue recently with solving linear systems of interval equations. The static arrays package changed their implementation of backslash, and that actually resulted in some breakage in our package, which so it's pretty delicate, these interactions. That's why you need lots of tests. Okay, so you can implement intervals in the standard way, just do a struct and you overload the operators. Everybody knows how to do that, so I won't go into it. But it's super efficient, right? So when you do the @code native of these things, you don't see any of the nonsense about the fact that it's a struct. You just see the sum of two tuples. And so as I said, the outward rounding is using now some completely different method that's not setting the global rounding mode. It's a package that Jeffrey Sarnoff wrote called error-free arithmetic, which is used for double doubles as well. So for example, what is the sum of the floating point number 0.1 and the floating point number 0.3? Well, it's the floating point number 0.4, except that it isn't quite, right? Because these are all approximations for real numbers. And so, in fact, it's actually the floating point number 0.4 plus this tiny little error. And so this tiny little error is telling us whether the true result of those things is below or above the floating point number 0.4. And then that tells us in which direction we need to round to get rounded plus, right? So then, using that, we can sum these two numbers with rounding downwards, and sum these numbers with rounding upwards, and that is going to give us the way to bound rigorously an interval using floating point arithmetic. And this is surprisingly fast and thread safe, although I don't have an example with threading yet. Okay, so there's lots more technical things to do with rounding, but let's move on. So mincing is, so let me just go quickly. So here's a function, and what I'm doing is evaluating the function on this big interval, and that gives me some big interval that's an overestimate of the true range of the function. Now I'm going to mince that function. That means I'm going to split it into n pieces. I'm going to change n and see what happens. And the answer is, hello? Well, the answer is, it gets a better and better approximation of the function. So, when people say, oh, but interval arithmetic gives you a huge overestimate of the function, well, you just split it up into smaller pieces, and then you get a less overestimate of the function. And here I've colored the boxes according to whether they contain 0 or not. And so anyone that does not contain 0, if you're looking for a root, you just throw it away. And so that's the way you start to locate zeros of functions. So for example, here's, okay, none of this is working right now, so let's just skip over that. Okay, I can do guaranteed integrals in one line of Julia. So this is like a Riemann integral. So this should be taught at first year undergraduate level, that you can use interval arithmetic to do rigorous integrals doing the standard Riemann thing, which is a lower bound and an upper bound in one line of Julia using intervals. So there, for example, is the integral of the function x squared over the interval 0 to 1 with 100 sub-boxes, and it gives me a result. There should be a third, and the result is that it's guaranteed to lie within this interval. And then I can just add more and more boxes. Of course, it takes longer and longer to do that calculation, and it converges to an interval that contains the true value. So let me finish by talking about some of these algorithms. So I still didn't get to constraint propagation. So how do you do interval bisection? There's the algorithm. Basically, you have a working list of boxes. You take one of the boxes. If it's too small, then you don't know what's going on, and you put it into this list of don't knows. If you can prove that there's no 0 in the box, then you delete it. And otherwise you bisect it and push the two resulting things back into the list. And so that translates into this piece of Julia code, which once you've defined all of the operations, works in n dimensions. Right, so this is like the simplest interval bisection algorithm, which guarantees, once you've spent 4 years writing interval arithmetic, it guarantees that you can exclude regions where there are no roots, and give you the regions where there are roots. And so then we can do the same with global optimization. So here's the equivalent for global optimization. The only difference basically is that now you keep track of the current estimate of what your current upper bound of what your global minimum is, and any box which when you evaluate the function on that box is completely above that global minimum bound, you throw it away. That's that algorithm, and that translates into this piece of Julia code, which is basically what's written in the interval optimization package as it was before Sheehan took over. And this completely naive algorithm is what you saw just minimizing a 50-dimensional function in 2 seconds. And here's an example with a pretty nasty function with lots of minima, and you can optimize it. And it turns out that, yeah, there are several minima of this function, global minima with exactly the same weight, and you can find them all. And so I do want to mention constraint propagation. So how do I find this set of things, which is all the set of points which are x squared plus y squared is less than or equal to 1? What I'm going to do is start with no information. So x and y are both intervals from minus infinity to infinity. Then I'm going to introduce at the node, so I'm going to think of this expression as a tree, an expression tree, and I'm going to introduce at each point of the tree a new variable. So a equals x squared. It knows that when you square the real line, the result has to be positive. B is the same. Uh-oh. And then c is x squared. C is a plus b, which is x squared plus y squared. And so then I need to impose this constraint. How do I impose a constraint? I say, oh, well, the new value of c is going to be the old value of c intersected with the constraint region. And then the thing is that, okay, now a is equal to c minus b. But the current value of a and the current value of c minus b are not consistent. So basically, a is too big. There are regions of a which are not contained in c minus b, and vice versa. So I'm going to propagate the constraint information down the tree to a by doing a equals a intersect c minus b. And to finish off, x squared equals a, that's how we define a, and so I have to invert the sum. Here I'm inverting the plus operation, here I'm inverting in a set sense, right? I'm finding the set of all things which satisfy this sum equation. So here I get, I'm inverting the square operation, and that gives me this little interval. So I started with the whole plane, and I propagated this constraint information, and that shrunk the box down. So so this operation gives me something called the forward-backward contractor, which takes a big box and contracts it down by excluding regions which I can guarantee are not contained in the set defined by this inequality. And so that's what all this contraction at the start was doing, and that's what the constraint optimization does. It puts this contraction step inside the global optimization code that I just presented. So I think I'll probably stop there. So we can now almost do constraints involving derivatives. We need a better API, and then we need to interface the packages with Jump. Of course, we need better documentation, and we need your help. In particular, we welcome hard test cases of functions that are difficult to find roots of or optimize. Yeah, so thanks for your attention. Any questions while we set up? Sorry? So the method is that you take these contractors and you insert a contractor inside the global optimization routine that I presented. The global optimization is just calculating the image of a box and checking if that image is above the current global minimum and updating the current global minimum if the box is lower than the current global minimum. And now I'm just inserting an extra step, which is contracting this box. And if I can prove that the whole box is outside the feasible set by using this contractor, if it contracts to the empty set, basically, then I just throw away the box, because I know it's outside the interesting set.
So you're not really... Okay,
I'm not doing anything.
For the function that you had, which happened to be convex optimization, you weren't really using the fact that it was...
No, I don't use anything about convexity.
It was global no matter what the
Yeah,
function was.
yeah.
But because I think you could also just write the KKT conditions and so on.
Yeah, so another way to do this is to write down the KKT or the John conditions and find the roots of those, and we need to implement that as well, yeah. But that will also benefit from this constraint propagation,
Right.
we believe. More questions? Yeah.
Which functions can be used? Because we have to do it by hand and control everything.
Yeah, so the question is, which functions can be used? And the answer is, we have a certain subset of functions already implemented, for example, sine and cos. Any more complicated function, like special functions, you would have to implement an interval version of the special functions. So, yeah, that's not so obvious to do, and that's definitely restricts the usability. So if you can represent them as Taylor series, for example, then like our talk on Friday will partially answer that question. We were discussing that with Sheehan as well. Yeah.
Okay. Let's see if I can quickly put this on. If this doesn't work, I'll just, I think I have a pretty loud voice. Actually, you know what? Let's go like this. Hi, my name's Mikhail Slavinsky, and I'd like to talk to you about fast transforms. If you were here for the first session by Sheehan Olver, or the first speaker, he would have mentioned this. It's a plug-in package to the approximation ecosystem, and it's sort of unusual in the Julia sense where, I mean, it does use types, it does use multiple dispatch, it does use all these fancy things, generated functions, macros, but the main product is literally just a set of functions. Okay, so the reason is approximation is a unifying package that gives you the ability to work continuously with functions and as you would with vectors and freely. And this package does a lot of the high performance transforms that are required for working with more exotic bases in particular. And the reason it's a different package is because if you are working in a high performance environment and you don't want all of the wrapping, then you don't need it, right? Okay, so what does it offer? Well, the first thing I'd like to do is thank contributions from Sheehan, Alex Townsend, and Michael Clark. It offers three things. One-dimensional orthogonal polynomial transforms. So the poster child would be transforming Chebyshev series to Legendre series and back. Or Jacobian more generally. It offers non-uniform fast Fourier transforms. So there's three different types of these. So there's non-uniform points, there's non-uniform frequencies, and then there's both. And it offers two-dimensional harmonic polynomial transforms. And these are markedly different than 1D otherwise. I mean, I wouldn't just list them as as orthogonal polynomial transforms because the algorithms are different. Okay, so what are the algorithms? So there's many references to this. I normally give math talks. I don't think I've given a software talk on this before. So there's many beautiful algorithms. Here are just sort of representative references for each of these. So the fast multipole method, or an adaptation for the connection problem, so Chebyshev to Legendre transform. The butterfly algorithm was developed, theoretically by Rocklin and his group. The fast asymptotic method, this is basically using the fact that Chebyshev polynomials are local, all orthogonal polynomials are localized in frequency. And also another way of looking at the connection coefficients using the fast Hadamard product. Now one of my sort of motivations for Julia was actually that there are so many beautiful algorithms. Which should the user actually use? And a lot of the literature is not very clear because there are different cases where some of the algorithms have different characteristics, but are independent. For instance, of the problems at hand. So the fast multipole method, for instance, has been generalized and used throughout essentially integral equations, boundary integral equations, and many other different applications, eigenvalue problems. But in terms of orthogonal polynomial transforms, it actually has very little pre-computation, so it's extremely competitive. But all of these algorithms have different characteristics. Okay. So here's just a slide on sort of some of the applications that you can think of. So they're all essentially mathematical, but the ones in bold are the ones that I'll show you some applications today. So 1D orthogonal polynomial transforms, they're useful because convolution of two polynomial series is actually a banded operator when you view convolving one with another when you use Legendre polynomials, right? So you want to actually work with Chebyshev because you've got the fast transform to the grid, but then you want to go to Legendre every once in a while, right? Similarly, singular integral operators, so Cauchy transforms, Stieltjes transforms, log transforms for boundary integral equations, these are actually just a change of basis, and then they become some hypergeometric function that uses a different set of tools. But essentially, when you work with the right Jacobi weighted polynomials. Okay, non-uniform fast Fourier transforms. So one reason you might use this is a semi-Lagrangian time-stepping scheme for advection. What you do is you just imagine a bunch of particles on an equispaced grid. You just sort of move them along where the characteristics want to take them. And then you take that information, you propagate it backwards, and then you use that and then you have to evaluate on that grid. So essentially that becomes a non-uniform problem. And then I'm going to show you this unusual example. What is a random function? And the idea is we're going to eventually get to the Chebyshev series of this random function. And then, of course, 2D harmonic polynomial transforms. This is what I've been essentially, in terms of my research, this is what's been essentially what I've been focused on the most. These have huge applications. Numerical weather prediction, sky's the limit, CMB, right? But it's not just spherical harmonics, it's also triangular harmonics. And here, this is obviously one of the cornerstones to a fast spectral element method. And the example I'll show you is a live solution of a time-dependent PDE on a sphere, reaction diffusion, with a nice Rolls-Royce exponential integrator. Okay, so if you're just starting to begin using fast transforms, take a look at the README. It will show you the basic interface. Okay. If you want to delve deeper into actually what the mathematical definition of the functions, at least the primary ones, are, then read the documentation. There's an examples folder, and we'll actually look at one of those examples, and two other examples are, well, one's not available, and then the other one is in a different repository. And then, of course, if you start to get really interested in this stuff, take a look at the references, which are at the end of the README. Okay, so what is a random function? So one way that you could actually define a random function is take is the Paley-Wiener series. And it's basically you just take linear combinations of the eigenfunctions of the Laplacian, right, on the domain. Right? So let's just take the interval 0 to 2 pi. And then our eigenfunctions are just going to be complex exponentials. And now we just take the coefficients. Oh, sorry, this should be an AK. The coefficients to be normally distributed with mean 0 and variance 1, and then some scaling which depends on the sort of size. And so here this n is sort of a frequency or a wave number limit to our random function. And what it will do is it will look uniformly bumpy. Okay, but that being said, it might not be convenient for us to actually end up with a Fourier series. We might actually want to have a polynomial representation of this so that we could use this as the right-hand side or the input to a differential equation. So what we're actually going to do is we're going to use essentially, so this is the definition of the NUFT, and it's basically, it's not, all of the numbers here are completely different, but I mean, as you can see, it has a very similar form. Here it has positive and negative frequencies, but that's just a diagonal scaling, and here it just has negative frequencies. And the points are in 0 to 1. Okay, so let's just see how that works. So what I have is I have two functions. Okay, so I think I have preloaded this. So basically we have this function here, Laurent to Chebyshev, which essentially does that directly, and which is slow, right? Because it's going to take an amount of time that depends on the length of your representation times the size of your grid. And then what we do is we end up with essentially an approximation fun in the Chebyshev space on the same domain, well, on a aperiodic version of the same domain. And then with just, a couple extra lines, basically right here, instead of going vals is equal to f at x, if we use vals is equal to the type 2 NUFFT, right? And then use this diagonal scaling, and then we also sort of extract the coefficients in this weird way, which is related to this, there's a two-sided diagonal scaling. We can actually do the same thing with using this fast technology. I'll show you how this works. So basically, let's just take n is equal to 201, just for now. Okay, and then we go f is equal to fun in the Laurent space. Okay, and then we'll create complex, and then we'll use rand n. We'll use n of them, and then we'll go rand n. And then we'll divide by that scaling, which is just essentially related to the number of coefficients that we use, right? And divided by 2 because we're using complex in the square root, okay? And now what we can do is we can create g is equal to Laurent. We'll just call that function. So we'll just call g is equal to Laurent to Chebyshev. Okay, so that was reasonably fast because, it's just 201 Fourier modes. But we'll see, we'll go 10,000, 100,000 in a second, and we'll see how the NUFFT is sort of, is it here? Okay, we can do the exact same thing with the NUFFT, and we can check, because we now have two Chebyshev representations, we can just go norm of g minus h, and because it's in this approximation framework, we get that we have obtained comparable representations down to roughly machine precision. And of course, there's no verified things because we want to do things fast, right? But the mathematics holds true, subject to the working precision. Okay, so what is the function? So if we plot the real part of our uniformly bumpy function, this is exactly what we get, right? And it has roughly mean 1 or mean 0 and variance 1. Okay. But just to sort of prove the point that we actually have a Chebyshev representation which actually looks like f, here's the real part of g, right? And then, of course, the real part of h, the one that's obtained by the NUFT, they're all essentially right on top of each other. Okay, so here let's just take, I guess one of the demos crashed earlier at 10,000 points, so let's just show that this stuff does actually scale. So here what we'll do is we'll create the same fun. I think we can just copy this line right here. So, all right, so this is a function which has 100,000 coefficients. If we did the Laurent to Chebyshev, it would basically it would take too long. So what we're going to do is we're just going to use the NUFT version. And if we call it on f, we see that, I guess this is using at time is supposed to call up the REPL. Maybe it's, it was pretty quick, wasn't it? Okay, so just to sort of end with a cornerstone on the fact that okay, this might actually be a little too large for the next part. But basically, if we take it down to 10,000, here we'll do the exact same thing. We can actually find the mean quite easily. And so we could just, okay, so it's complex, so we'll just take the absolute value of the sum. Right here, this is the integral, and then we'll divide by the domain. And we get its roughly mean 0, right? Subject to the noise, right? And then the standard deviation would be something like this. And getting this sort of scaling just right is, I guess, a work of art. So somehow it's something like this. And then if you just take all of this, and then inside here, divide by 2 pi. I think this should work out to roughly 1. Yeah. Okay, so this is how you can actually use the NUFT to represent uniformly bumpy functions. Okay, It's a kind of philosophical kind of thing, right? Okay, but now I'll show you an example which is a little bit more of a tutorial nature, and then the next one after that is going to be about high performance. Okay. So, spherical harmonics. So spherical harmonics, they're eigenfunctions of the Laplace-Beltrami operator on the sphere. They have this nice separable form right here, so they can be realized with Fourier modes, complex exponential, or the real sines and cosines. And then associated Legendre functions, and with this normalization we now have orthonormality in L2. Okay. One thing that we note is that they're actually essentially powers of sine times ultraspherical polynomials. Okay, and here this sort of normalization which relates associated Legendre functions to ultraspherical polynomials is just given in terms of the rising factorial. One thing that we'd really like to do on the sphere is synthesis and analysis. So synthesis and analysis just means take an expansion in spherical harmonics and rapidly evaluate it at function, like on a grid, right, a tensor product grid. And the same thing with analysis, convert function values on this grid to spherical harmonic coefficients. The reason is in physics we like this duality between momentum and physical spaces, and we sometimes need both to propagate a partial differential equation. So naively it's n to the 4, where little n is the degree. But of course it can be trivially reorganized to n cubed, and sort of what we're looking for is n squared and some polylog term right here, some amount of logarithm is acceptable. There's a rich history on this. Lots of people have worked on this. But it sort of left a lot of questions open when I started taking a look at this. The first question is, everyone always goes straight to the grid. But I'd like to give users more flexibility, mathematicians as well. And so the idea was, why not just go to a different basis, one that we could actually use a little bit more conveniently. And then nobody actually came up with a numerically stable algorithm that was proved numerically stable on paper, right? Okay, so what is the solution? The solution is actually to change the problem. We actually know that if we can use a Fourier series, so here I mean like a tensor product, just sines and cosines in theta and phi, right? We've got the FFT, the DCT, and the DST at our disposal. We have non-uniform variance, right? So we can do all sorts of nice things once we get to a bivariate Fourier series. And the idea is that the associated Legendre functions, in fact, are, well, for even m, they're cosines. There's cosine series. And for odd m, they are sine series. So we know that we can do it. And there's a nice connection here between sort of expanding these associated Legendre functions into Fourier series with the Driscoll-Healy 2n squared sampling theorem. So this is sort of a diagram, and I'm not going to get into the algorithms because usually that would take up a whole talk. But basically here we go from really high order associated Legendre function expansions to order 0 and 1, right? And then we take those and we use the 1D technology. Like these are essentially the Legendre series, and then we convert them to Chebyshev, right? And then this part right here proceeds with the butterfly algorithm, and then this right here uses the fast multipole method. Okay, so one really cool thing about spherical harmonics is that PL of x dot y, where x and y are two unit vectors in R3, essentially points on the sphere, are actually given in terms of a sum of exact degree L spherical harmonics. Right, so this is a sum over m. Another thing is, so basically we can use this sort of reasoning to show that this function right here, PL of z dot y minus PL of x dot y over z dot y minus x dot y, it looks like a rational function, but as long as you replace it with when z dot y is equal to x, like the singularity by its calculus limit, right, the derivative, then this is actually a degree L minus 1 polynomial on the sphere. So I'll show you an example. So this is the tutorial type example. And then the next example is sort of about performance. And this will show you how. So if we have if we're looking for a degree 4 polynomial, say, we would need 5 points at least in angle, in the colatitudinal angle, to essentially resolve this function. So essentially, if we start by going n is equal to 5, and then what we could do is we could set up our theta grid to be 0.5 to be n minus 0.5 all the way down to, or divided by n. I don't know why that skipped. Okay, so just essentially what I'm doing is I'm modding the grid by pi because we can get slightly more accurate result. And then what we're going to do is we're going to use a 5 by 9 grid. So the reason is this is essentially related to sort of the degeneracy among spherical harmonics of a particular degree. So here I'll create this 5 by 9, or the 9 grid. So here we have 0 to m minus 1 times 2 over m. And this, I don't know why it keeps doing that, but anyway, this should be roughly between 0 and 2, because then from here we just multiply by pi and then we go all the way around the sphere. Okay, so we have 3 vectors at play, right? We have x, y, and z. So why don't we just take one, and it'll be useful because we can look at this multiple different ways. We'll put it at the north pole, okay? So here's one vector. Another vector, what we'll do is we'll just say it's 1, 2, 3, 4, 5, 6. This number works. So what we'll do is then, of course, this number is not actually, this vector is not actually on the sphere. So what we'll do is we'll just, I think we can, this should just work. We can just normalize. Okay, so this vector should be on the sphere. So then z is actually our variable, right? And we'll actually write this in terms of the 2 angles. So here, this is just sine pi of theta. This is the x, right? So then times cos pi of phi, sine pi of theta times sine pi of phi. And then this is the z variable, cos pi of theta. Okay, so there's that lambda. Let's work with a degree 4 Legendre polynomial so that this conforms with our grid that we've chosen. So this polynomial here is 35 times x to the 4 minus 30x squared plus 3, all that divided by 8. Okay. And here what we can do is we can say f is equal to p4 of z of theta and phi. I'm just going to copy this so I don't have to do it many times. So c dot y, okay, minus p4 of, what would it be, x dot y, right? All this divided by z of theta and phi dot y minus x dot y. Okay, and we'll do this for theta in theta and phi in phi, right? I hope this works. This is unexpected syntax.
You don't want the comma before the 4.
Oh yes, thank you. Okay, so let's just take a look at our, okay, so we just have some grid values, whatever they are. Once we do the analysis, we're actually going to be able to sort of get some meaning out of these, which is why spherical harmonics are cool. Okay, so what we need to do is we actually need to write 2 things that are part of fast transform. So one is plan SPH to Fourier. This is one of the products. Okay, and we'll call it with F, the matrix that we actually want to transform. And then PA is going to be something that it's not quite yet decided on the user syntax. So right here, I'm just showing you what it could be like. And this is just plan analysis on the sphere. Okay, so this is going to create 2 types, right? And we're going to be able to use these types. So the first thing we're going to do is we're going to say V is going to be, we're going to initialize it to 0, the size of our function values. And V is going to store the Fourier coefficients. And then once we go from Fourier coefficients, we'll go to spherical harmonic coefficients. So this should be V is equal to 0. Then we'll go A mul B, and then we'll go V, plan analysis, and F. And then once we do this, then we'll go U3, anticipating that it's actually degree 3, is actually P, the spherical harmonic plan, or sphere to Fourier. Well, we're actually using the inverse of this, so P backslash V. So if we run all of these, let's see what the output is. So this is a, does this work? Okay, this is a 5 by 9 array, and what I want you to pay attention to is actually the last number right here. That's the degree 4 coefficient, which should be there, right? But we've demonstrated that this is actually a degree 3 polynomial, right? All of these ones, the last entry of every column is actually roughly machine precision, or on the order of. Okay, so what I'll do is I'll show you that actually this function right here, f, let's just see how we're doing for time. Okay, I'll just quickly show you that if you align f to the grid, you get exactly what, and we just look at this degree 4 polynomial, we know exactly what we should get. We should get one coefficient, right? Non-negligible coefficient. So if we redefine f to be that, and then we just take this code right here, and then we go U4, and then we go like this, and we take a look at those coefficients. All the high order m modes are 0, and the m is equal to 0 mode, they're all machine precision except for this normalization right here, and this normalization is actually related to the orthonormalization. So it's actually square root 2 pi over 4 plus a half, right? So if we take a look at that, we get exactly that 1.1816. Right. Okay, so fun with spherical harmonics. Now I'll show you essentially a supercharged example. What we're going to do is we're going to solve a reaction diffusion equation on the sphere. So right here, these are really popular because they clearly illustrate to you where the linear operator is, but it's typically stiff, and where the nonlinearity is, and where you evaluate that on the grid, right? So the example we'll show is the Allen-Kahn equation. The Allen-Kahn equation is used to model phase separation in alloys. Recently work with Hadrian Montanelli and Kang Du at Columbia, we actually took a look at a drop-in replacement for diffusion with non-local diffusion. And we actually get more physical results, which I'll show you in just a second. The idea is that phase separation in alloys should actually asymptotically end up, separating. You should end up with a discontinuous solution, right? But when you run the Allen-Kahn equation, it has metastability, which is great, between plus or minus 1, but eventually 1 wins, right? And so you never actually asymptotically separate the phase. Let's see. So this example, I want to show you that these are multi-threaded. To make sure of that, I actually run it in the terminal. And I'm using Mackie, which is fantastic. Well, I'll let you decide. Anyway. So here all of this stuff is loaded. This is a poor man's version of essentially all of the types that you'd need to create like an object that represents a semilinear PDE. And then once you do this, then, okay, here's the fun. So essentially all of this up here is going to be setting up the initial condition. The eigenfunctions of the Laplacian right here create a uniformly bumpy function, right? So the eigenfunctions of the Laplacian on the sphere are spherical harmonics. So if we just take a look at those, I guess we get a uniformly bumpy function, right? If we took away the axes, I mean, I don't think you could tell me where the poles are, right? That's one way of sort of thinking about it. Okay, and now let's see if everything else works. So here what I'm using is I'm using ETD RK4. This is a great exponential integrator. I'm going to integrate it for 8 seconds. Not looking for particularly high accuracy right here, just 6 time steps per second. But ETD RK4 has amazing accuracy. So if you use that, I think at least from one time step to the next, the physics are approximately right. So here, this is actually the classical one with a particular value of. So this is happening live, right? Okay. So yeah, fun with spherical harmonics, right? Okay, and then Mackie, you can make a GIF. So you can save all of this. So I think it's here. Oh, you know what? Okay, you know what? Let's take a look at this. So, right. So this is your nice finished product, right? And you can see how it's coalescing. You have to go for an exponentially long time scale before you see +1 or -1 win out. I don't know which one wins out in the end. It kind of looks to me like -1 maybe, like purple. But now what we're going to do is we're going to repeat the exact same experiment, trying to be a little bit more physical. We're going to use non-local diffusion right here. So let's just run it. Yeah, and it does mathematically tend to a discontinuous solution, right? And that's somehow what we expect for sort of a phase separation in alloys. If you have a keen eye, what you'd see is that actually there's some ringing, right? Because if you just take the Fourier series of a discontinuous function, you get the Gibbs phenomenon, right? And this is the Gibbs phenomenon in 2D. However, like when we wrote this in the paper, I'm just showing you this now, but if you can add a filter.
What are we looking at?
Oh, you just look at these little, can you see it? Let's okay, it's really hard to see with, anyways, there's a Gibbs phenomenon. It just shows that. So if you look here, basically what there is on this computer screen, you would see oscillations in the plateaus, right? But you can smooth those out with a global post-processing called Cesaro summation. It's great in theoretical analysis. And that's it. Thank you very much. I'll be around all week for questions.